Good evening, everyone. We are welcome for this lecture, BCH 322. I didn't know nobody is on Zoom. I've been waiting to see you on Zoom. I can't see anyone because I've launched the poll. You're supposed to sign in on Zoom and log in on Zoom to sign in your attendance. But my information is getting to be that some of you are on YouTube. Is that correct? Okay, I'll just wait some more minutes. I'll wait some minutes more. Okay, our class for today, the topic for today's class is techniques in protein biochemistry. And protein biochemistry is talking about the chemistry of enzymes, the chemistry of proteins, that is, how to get to the simplest unit of the protein. Now, what are the techniques that are often used in protein biochemistry? That is exactly what we are here to find out. I'm trying to go back to Zoom. Great. So by the end of this lecture, we hope to have been able to get 1 or 2 points on each of these separation techniques. Now, protein extraction and homogenization. Like I said, to know the type of amino acids that make up a protein, or the simple units of a particular protein, there must be extraction. And so the first technique in protein biochemistry is extraction and homogenization. What do we mean by extraction? Extraction is a method of releasing the cellular components from a cell. The cell wall is the envelope of all the cellular components of a cell. It's envelopes and what will I use? All the components within a cell. If you can say trap. So for us to get the protein of interest, the cell wall must be broken. And how do we break the cell wall? because proteins are very delicate, care must be taken not to denature or destroy the protein of target. So there are different methods used in disrupting a cell membrane. Mechanical homogenization is often used. That's use of a blender. Please note, depending on the protein of interest, because some proteins, it's often said that once the protein loses its structure, it loses its function. So that means the scientist or the researcher must have studied at length the protein of interest to know its conditions that are favorable and conditions that may be unfavorable. So the first method is mechanical homogenization using a blender or mortar and pestle. And this is often used for soft tissues like the liver or the brain. The next method for disruption of cell membrane is sonication. This is the use of high-frequency sound waves to break the membranes. And this method is used for bacteria and cultured cells. The next method is the Freeze-Thawing cycling. The Freeze-Thawing cycling, and it's a repeated freezing method. When the organism is frozen to maximum temperature, to the lowest room temperature, and it allows to thaw, the cell walls break and all the elements within comes out. So this method is used for gentle cell disruption, where you don't want to damage the organelles within the cell. So the list continues. And after homogenization, we have the next method is prevention of protein degradation. How do we prevent the protein that has been extracted from within the cell wall? How do we prevent them from getting destroyed? Number one, I said, if you remember at the beginning of the lecture, I said the first is to know the working temperature for each of these samples. Most proteins, they work best at 4 degrees Celsius. That means you must work in ice. Number two, to prevent the protein of interest from being degraded, because once the cell wall is disrupted, everything within the cell organelle comes out, including other enzymes. So addition of protease inhibitors, that is enzymes that will inhibit the breakdown of protease. Protease is an enzyme that breaks down proteins. So addition of protease inhibitor. pH also is key. Maintenance of appropriate pH. Avoidance of foaming, because it's also denatures protein. And addition of reducing agents. So these precautions must be taken to ensure that the protein of interest is the target and must not be disrupted before we get to the end of the experiment. Now, after we've just broken the cell wall and we've secured the protein of interest, what separation techniques will we now use? Because it's a total package. Every cell within the cell wall is also in the medium. So how do we get the protein of interest out of the solution that we now have having disrupted the cell membrane? One, we could use centrifugation techniques. And these techniques, centrifugation is a technique that separates based on size, shape, and density. And this is the formula. RCF equals to 1.12 times R times RPM. Now, there are different types of centrifugation. We have differential centrifugation used for subcellular fractionation. The next type of centrifugation is the density gradient centrifugation. And this one occurs in two forms. You have the rate zonal, used for separation of particles by size and shape. And the other one is the isopycnic, which separates RNA and DNA molecules within a sample. The next separation technique is the ultracentrifugation. This one separates based on molecular weight of the sample. Then the next separation method is the chromatography. What is chromatography? Chromatography is a method that separates proteins based on differential migration through a stationary phase. You have a column is set up. The sample of interest is run through the column, and the one you set the column in a way that the sample of interest is trapped within the column, and all the ones that you're not interested in is eluted, is run out, so that at the end of the day you can now remove your sample of interest from the column that was set up. So chromatography separates based on differential migration through a stationary phase in a mobile phase. Then we have ion exchange chromatography. From the name, we can know that this one has to do with cations and anions. So negatively charged resins bind positively charged proteins for cation, and for anion exchange, positively charged resin binds negatively charged protein. This separation technique is used majorly for purification of enzymes, antibodies, or plasma proteins. Now we have gel filtration. Gel filtration is a separation technique used to separate protein by molecular size, whereby the large proteins elute first, followed by the small proteins. And it's important to note that a ladder is what the ladder, that's the standard, is used so that you know where the band for the protein of interest lies. One must have good information on the protein of interest so that the right ladder is used and the right band formed. Now, I want to harvest questions at this junction. Is there any question? Am I too fast? Am I too slow? I need to be sure that we are communicating, that I am communicating. Are we here? Or I've been talking to myself? Okay, thank you. So continue. Now, we said we have the gel filtration is the fourth type of separation technique we have. Then the next is the affinity chromatography. It separates by biological binding specificity. That is, the ligands are covalently, that means permanent attachment to the resins, and only the target protein binds specifically. and diluted either through change in pH or specific eluting agent. The next we'll be talking about is the hydrophobic interaction chromatography, which separates by surface hydrophobicity. And the next to that is the HPLC, which is a modern technique. HPLC is high performance liquid chromatography, and it uses high pressure to force the mobile phase through tightly packed columns. So this purification table is showing each protein, every protein purification is tracked by a purification table, and they all have different specifications by which they should be monitored, at which they work. Because if you do not use the specification for a particular protein, you will not get the right result. Now, the next technique for purification of protein is the electrophoresis. An electrophoresis technique separates by charge. Then the next we'll be talking about is the SDS page. That's the sodium dodecyl sulfate polyacrylamide gel electrophoresis. It's a type of electrophoretic method commonly used in labs worldwide. Let me just dwell a little on this. So the SDS, that's the sodium dodecyl sulfate, is an anionic detergent that denatures proteins and coats them uniformly with a negative charge. And still contained, and still within this method, we have the beta mercaptoethanol, which is used to break disulfide bonds or reduce the bonds. Now, all proteins have identical charge to mass ratio, and separation is purely by molecular weight. So by molecular weight, depending on how heavy or light the protein is, smaller proteins migrate faster, while the larger proteins migrate later. They come behind the smaller proteins. Okay. So for one to use the SDS page, the sample must first be prepared by boiling with SDS and beta M eloding buffer, after which this mixture is run through gel electrophoresis. And then in course of the gel electrophoresis, there is a staining with Coumadin blue or silver stain. The staining is to be able to visualize the separation bands clearly and be able to easily identify the protein of interest. Okay. And then, depending on the migration bands, each band, the mark on each band is now compared with molecular markers in literature. That will help us to know what protein is present within, or if we got the right protein. Okay. So each band is a protein or a protein subunit. Band positions depict molecular weight, and band intensity is equivalent to amount of protein. So much for the SDS page. The next separation technique we'll be talking about is the isoelectric focusing. Isoelectric focusing separates protein via the isoelectric points using the pH gradients within the gel. And in this method, proteins migrate until they reach pH where the isoelectric point or their net charge is equal to 0. At this point, proteins stop migrating, and then there is a sharp focus band that is formed. And this helps us to know or locate or identify the protein being examined, being the protein under investigation. Then the next separation techniques is the two-dimensional gel electrophoresis. It's like the name, there's the first dimension which separates by isoelectric points, and then the second dimension which separates by molecular weights. So this two-dimensional gel electrophoresis is used for high precision separation technique, like in cases of cancer or drug discovery or proteomic filing, when we need high precision results. This is often the method that is used. And then the next separation technique is the agarose gel. Agarose gel is used mainly for DNA and RNA identification and often for large protein complexes. The next separation technique is the spectrophotometric method. And this method follows Beer-Lambert's law, which says that absorbance is directly proportional to molecular coefficients and the concentration of the sample. So these are the various separation methods that are used. Now we have protein quantification. Now, having been able to remove the protein of interest, how can we know how much protein is within the sample? We've been able to extract the protein of interest through one or more of these separation techniques. Now, how will we now know the quantity of protein of interest? So the first is usually using the UV absorbance at 280 nanometer, that's the wavelength, for aromatic amino acid like tryptophan or thyroxine. The next, for quantification of protein, the next method for protein quantification is the Bradford assay, using Coumadin blue at an absorbance of 465 to 595. Now, each method differs depending on literature surrounding the protein of interest. Another quantification method is the Lowry assay. The Lowry assay occurs in 2 steps. First, the Biuret and Folin reagents are used, and the sample I used to prepare the sample, and the sample is read at 750 nanometer. And this method is quite very sensitive, but it takes quite some time, about 45 minutes. Then we have the BCA assay. The BCA assay is another quantification method. That's the bicyclonic acid. And each of these, you'll notice that the wavelengths are not the same. The wavelengths keep changing depending on the protein of interest. Then we have the Biuret assay. The Biuret assay is the reaction of a protein with copper ion in an alkaline solution, and a purple complex shows the presence of protein, and the quantity can be calculated when the sample is run under the spec at 540 nanometer. Now, there are also immunological techniques. Immunological techniques are techniques that are used when you really want to know the exact specific protein present. And that's why it's used for antigen-antibody interactions. So the first immunological technique is the Western blot. This combines SDS page with immunological detection. And this technique is often used for the HIV test. It's used as confirmatory test for to know if the person is HIV positive. It's also used as to detect specific proteins in research. So you have the Western blot is equals to SDS page plus transfer plus antibody detection. Then the next is ELISA for the immunologic techniques. Enzyme-linked immunosorbent assay is quite sensitive, highly sensitive. And what does this technique do? The ELISA are of 4 different types. We have the direct ELISA, the indirect, the sandwich, or the competitive. Now, these tests are used majorly to identify specific, what will I call them? Reactants in a sample. They are used for HIV tests, pregnancy screening, COVID, hepatitis B, and like the homework I have beneath this table, please make sure you submit it before next class. It says what components in the sample and test strips is reacting to give us the results we are looking for. So please note the assignment. And then the next quantification method, having separated a protein, is the immunoprecipitation. This happens when a protein is subjected to conditions that do not favor it. So it forms salts. That's the salt that is precipitated out of the solution. And that's a way of also extracting the protein of interest. Then there's the immunochemistry method, where an antibody is allowed to react with an enzyme. And this is used to locate proteins in tissue. So now, those are some techniques. Now we have the advanced modern techniques. One of the first advanced modern technique is the use of mass spectrometry. Mass spectrometry is a method that identifies unknown proteins, post-translational identification, or post-chain interaction. And what happens in this method is the proteins are ionized and separated by charge, after which a protease digestion is introduced into the solution, and the function of this protease digestion is to break down the peptide bonds so that the amino acids could be released to break protein into its monomeric form to release the amino acids. And clinically, this method is used for microbial identification. If there's an investigation on a type of disease or invasion into the system, into the body biological system. Then we have the X-ray crystallography. The X-ray crystallography is used with quantification of proteins using the crystal diffraction X-ray, and it reveals the structure of hemoglobin, myoglobin, DNA, of polymerase antibodies. We also have the NMR, nuclear magnetic resonance, and it determines the 3D structures and protein dynamics. We also have the cryo-electron microscopy. It's the fastest growing technique, and this method resolves the structure of large complexes like the ribosomes or the viruses without crystallization. Then you have the flow cytometry, and it's used for CD4 and CD8 T cell counting in HIV monitoring. Okay, so we'll go to the next quantification method, the X-ray crystallography. The X-ray crystallography measures static 3D atomic structures near atomic resolutions, but has some limitations in that the crystal lattice may constrain natural flexibility. But it's a fast-growing method, and I'm sure in a month with time, that setback will be overcome. Now, the NMR spectroscopy measures 3D structure and dynamic solutions. Okay, so let me just use this table to summarize each of these techniques. So from the table, we see that each of these techniques, they have their strengths and they have what they measure. So depending on the protein of interest, each of these techniques also are complementary, meaning that one or two of these techniques are often used to get to the point of best of interest and the sample of highest precision. Now, how are these techniques, how are they applicable to our day-to-day life? Why are we disturbing ourselves about protein separation techniques in protein biochemistry? Number one is based on these principles that patients get treated. Take, for example, the STS-Page Western blot is the technique that is used for confirmation tests for HIV patients or patients with neurodegenerative disease proteins. The ELISA also is used for HIV screening, hepatitis, pregnancy, or cardiac markers. Then we have the serum protein electrophoresis. Clinically, it's used to identify issues related with multiple myeloma, nephrotic syndrome, or cirrhosis, that's liver cirrhosis, damage to the liver. So each of these methods is specific, highly specific in treating one ailment or the other. Now, in summary, these are the separation techniques listed, and we have what they separate. Centrifugation separates based on size and density. SDS fish separates based on molecular weight. ELISA separates based on antibody antigen specificity. I would like to know by this time, this Friday, let's say latest by Wednesday, I would like us to turn in this assignment. Latest by 12 midday on Wednesday next week. Please turn in your assignments. There are 2 assignments in this lecture material, and I would like to harvest your question. But in the absence of any question, I think it's time we call it a day. Okay, and at this point, we share the grace. May the grace of our Lord Jesus Christ, the love of God, and the fellowship of the Holy Spirit be with us all ever and ever. Thank you. Enjoy the rest of the day. Bye.